very expected example we are going to start. Example: determine a function which shall be regular within the circle mod z equal to 1 and shall have on the circumference of the circle the value a square minus 1 cos theta plus iota a square plus 1 sin theta over a the power 4 minus 2a square cos 2 theta plus 1. We have to determine the function, and it is given that on the circumference we have the function fz is equal to this. The value of the function is this, and the function regular within the circle means all the terms are positive inside the circle. Inside the circle we are having the regular part, outside the circle we are having the principal part. So this example is telling us about that function is regular inside the circle. That means we are having the positive terms of the function fz. So let's start with the solution. What we need to do is we first have to get our fz function, right, in terms of exponentials, and then we have to go for the coefficient an, put the value of fz in that coefficient, we get some result, and on the basis of that result we get the required value, the function which we have to determine, right? So let's start. Let fz be the required function. Since fz is analytic inside the circle C mod z equal to 1, therefore fz can be expanded in Taylor series within mod z equal to 1 because all the terms are positive inside the circle. So we can write that this function can be expanded in Taylor series. So we have the function fz that is equal to, let me change the color, fz is equal to summation n going from 0 to infinity a n z the power n. This is your Taylor series containing only the non-negative terms, where we know that a n, the coefficient, is equal to 1 over 2 pi iota integral over c f of z over z the power n plus 1 dz, right? Now on the circle C mod z equal to 1, so we have f of z is equal to, yes, a square minus 1. This is given to us on the circumference of the circle. The value is a square minus 1 cos theta iota a square plus 1 sin theta over a the power 4 minus 2a square cos theta plus 1. Actually cos of 2 theta plus 1. Fine. In the next step, let's take a square common. A square cos of theta plus iota sin of theta minus cos theta minus iota sin theta over this denominator a to the power 4 minus a square. Now what is 2 cos 2 theta? This is equal to e to the power 2 iota theta plus e to the power minus 2 iota theta. This is the formula, plus 1. Now what we have to do is, we know that cos theta plus iota sin theta is e to the power iota theta. So a square e to the power iota theta, making the expression in exponential form, minus this will be e to the power minus iota theta. Alright. So this is a to the power 4 minus a square e to the power 2 iota theta plus e to the power minus 2 iota theta plus 1. Now 1 can also be written as e to the power iota theta e to the power minus iota theta. Can I write like this? Yes, of course I can write. So instead of this one, I am writing this so that I can take common. So this is e to the power iota theta into e to the power minus iota theta. You will get to know So this a the power 4, I can write a the power 4 e the power iota theta e to the power minus iota theta, so that I can get something common from the denominator and that will cancel out with the numerator, right? So on taking common something from the denominator, I get a square e the power iota theta. This is your numerator, e the power minus iota theta. On taking common, you can make the factors, and that comes out to be a square e the power iota theta minus e the power minus iota theta into a square e the power minus iota theta minus e the power minus iota, plus iota theta. Done nothing, just taking the thing common and get this result. So this first factor is cancelled out with the numerator, so I am lefting up with a 1 over a square e the power minus iota theta minus e the power iota theta on the circle, right? Now an is equal to 1 over 2 pi iota integral over c fz over z the power n plus 1. Now I am putting this value of fz in this an and putting z equal to r e the power iota theta in polar form. And I know that my radius is given to be as 1, because what is the circle? It is mod z is equal to 1. So radius is 1, hence z is e the power iota theta, right? And dz will be iota e the power iota theta. Let's put the values. 1 over 2 pi iota integral over c fz is 1 over a square e the power minus iota theta minus e the power iota theta, and this value z e the power iota n plus 1 theta into this dz, which is iota e the power iota theta. Okay. Now for the next step. Now this iota is cancelled out with this iota, right? So this is 1 over 2 pi integral over c 1 over, I am taking this a square common and e the power minus iota theta common. So this will be 1 minus e the power 2 iota theta over a square into e the power minus iota n theta. E the power iota theta is cancelled out with this numerator e the power iota theta. See, this is in the denominator, right? E the power iota n theta into e the power iota theta. This e the power iota theta will be cancelled with this numerator, and then this denominator is going to the numerator with their inverse, that is e the power minus iota n theta. Hope so this is clear to you. Which is equal to 1 over 2 pi, taking a square outside, integral 0 to 2 pi, because I am having the circle. So instead of c, I must write the limits for theta, that is 0 to 2 pi. And this is equal to e the power minus iota n minus 1 theta. And this goes to the inverse, e the power 2 iota theta over a square inverse d theta. See what I have done? Just taking this e the power minus iota theta in the numerator and summed up with this e the power minus iota n theta, right? And this bracket 1 minus e the power 2 iota theta over a square taking this to the numerator as its inverse. So this is a step. Next, now this is equal to 1 over 2 pi a square integral 0 to 2 pi e the power minus iota n minus 1 theta. I can expand this. Just take this as your 1 minus x the power inverse, which is equal to 1 plus x square, which can be summed up as x the power m. I am going from 0 to infinity because already I am having the variable n over here, so I have to write this in m. So summation, I am going from 0 to infinity e the power 2m iota theta over a raised to the power 2m. So this is the expansion for this. And why we expand this? We have to expand this for mod x less than 1. This is very important. Is the mod of e the power 2 iota theta over a square is less than 1? Let's check. Mod of e the power 2 iota theta over a square. This mod is equal to mod of e the power 2 iota theta is always 1 over a square, and this is less than 1. Right? So these are the reasons. Alright. Now in the next step, I would like to take this summation outside of the integral. Now when the summation can be taken outside? If the series is uniformly convergent. Now why the series is uniformly convergent? Because this is your GP series, right? So it is converging uniformly. Being the GP series, the convergence is uniform. So I am taking the summation outside. 1 over 2 pi a square summation, I am going from 0 to infinity, integral 0 to 2 pi e the power minus iota n minus 1 theta into e raised to the power 2m iota theta over a raised to the power 2m d theta. The convergence being uniform. Fine. Alright. Now what is the next step? See, there is a remark given to us, that is integration from 0 to 2 pi. Just revise this remark. This is helpful in further step. Integration for e raised to the power iota n theta and limit 0 to 2 pi. This integration is 0 if n is non-zero integer. Why this integration is 0? See, if I integrate e the power iota n theta, I get e the power iota n theta over iota n, and the limits from 0 to 2 pi, which is equal to e the power iota 2n pi minus e the power 0, right? Which is equal to, now e the power iota 2n pi is 1. Just open this, cos of 2n pi plus iota sine of 2n pi. So this value is 1, and e raised to the power 0 is also 1, which gives me 0. So whenever we are having any power in the exponential, having the integration with limits 0 to 2 pi, this comes out to be 0 if your power n is non-zero integer. Now in this expression, I am having the power 2m. So this is non-zero integer, right? So let's work on this. Now see, this integration, I take this, first I sum up this this power, e the power minus iota n minus 1 theta plus 2m iota theta. Let's sum up the power of e. So this is 1 over 2 pi a square summation. I am going from 0 to infinity, 0 to 2 pi. So I am adding the powers, exponential minus iota n minus, this is 2m plus 1 minus n iota theta d theta, and this is 1 over a raised to the power 2m. Just adding the powers of e. Now this 2m plus 1 minus n, this is any integer, a non-negative integer, right? So can you say this, if my n is not equal to 2m plus 1, then this integration is 0. See, if n is not equal to 2m plus 1, then this integration is 0. But if n is equal to 2m plus 1, then the power will be e the power 0, which is equal to 1. And what I got? I got then the result 1 over 2 pi a square into 1 over a the power 2m, right? Zero to 2 pi integration d theta. And because n is equal to 2m plus 1, I must write a the power as n minus 1, because the value for 2m will be n minus 1. So a the power n minus 1. Again in the next step, this is 0 if n is not equal to 2m plus 1, and this is equal to 1 over 2 pi a square into 1 over a raised to the power n minus 1. The integration for this is 2 pi if n is equal to 2m plus 1. So 2 pi cancel, what we get? Further 0 if n is not equal to 2m plus 1, and this will be 1 over, adding the powers we get n plus 1. So 1 over a raised to the power n plus 1 if n is equal to 2m plus 1. Fine. That means n is not equal to 2m plus 1 means n is even, and n equal to 2m plus 1 means n is odd. So for the even powers we are having 0 value. For the odd powers we are having 1 over a raised to the power n plus 1, right? So this is equal to 0 if n is even, and this is equal to 1 over a raised to the power n plus 1 if n is odd. That means we are talking about a n, right? That means a0 is equal to a2 is equal to a4. All these are equal to 0. Fine. And if I talk about a1, this will be 1 over a square, right? And a3 will be equal to 1 over a raised to the power 4, so on. So hence put the values in your function. What is your fz? We have to determine this function. Fz is summation an z the power n, and going from 0 to infinity, because for the even terms we are having this value to be 0. So this function will be z over a square, sorry, a1z, I should write like this. If I put n equal to 0, I get a0, z the power 0 is 1. So this will be 0 because a0 is 0, right? For if I put n equal to 1, I get a1 z plus, then again for a2 this term is 0, so this is a3 z square, so on. So which is finally equal to, put the value for a1, that is z over a square plus z square over a raised to the power 4 plus z cube over a raised to the power 6, so on. And we can write this as summation n going from 1 to infinity, and the nth term will be z the power 2n minus 1 over z the power 2n, because in the denominator we are having the even powers. So this is your finally summation. So here the solution ends up, we get fz to be equal to summation n going from 1 to infinity z the power 2n minus 1 over z the power 2n as our desired function, required function. Okay, easy? Fine. Let's move on to the next example. Find a function fz which is analytic throughout the circle C and is interior, whose center is at origin and whose radius is unity, and has the value a minus cos theta over a square minus 2a cos theta plus 1 plus iota sin theta over a square minus 2a cos theta plus 1, where a is greater than 1 and theta is the vectorial angle at points on the circumference of C. Vectorial just refers to that we have to take the values of z in the polar form, right? And the center is at the origin whose radius is unity. That means this example is also talking about mod z is equal to 1 as your circle, right? So again we have to find out the function for this. And now on the circumference, the value for the function given to be this. So since fz is analytic inside the circle C, mod z equal to 1, so fz can be expanded in Taylor series inside C. All the steps are same. Just we have done right now. All the steps are same. So fz is equal to summation n going from 0 to infinity an z the power n as a Taylor series, where an is taken to be as 1 over 2 pi iota integral over C fz over z the power n plus 1 dz. And on the circle, we know that mod z is equal to 1, this circle. We have to determine our fz. Now fz is equal to a minus cos theta plus iota sin theta over a square minus 2a cos theta plus 1. I take the denominator together with the numerator. So this is equal to a minus, take cos theta with this sin theta, minus iota sin theta. I took minus outside. So this is a square minus, again what is 2 cos theta? This is e raised to power iota theta plus e raised to the power minus iota theta. In the previous example we are having 2 cos 2 theta, right? Here I am having 2 cos theta, right? Plus 1. So this is equal to again a minus, this can be written as e raised to the power minus iota theta. And you have to take again the common things and you will get a minus e raised to the power iota theta into a minus e raised to the power minus iota theta. And one of the factors is cancelled out with the numerator and I am getting 1 over a minus e raised to the power iota theta as my result for fz. Now an is equal to 1 over 2 pi iota integral c fz over zn plus 1 dz. I have to put the value of fz in this an, and also z is equal to e raised to the power iota theta because r is 1 in polar form. So this is 1 over 2 pi iota integral. Now because this is a circle, now limits are going from 0 to 2 pi, and fz is 1 over a minus e raised to the power iota theta into 1 over z is e raised to the power iota theta, so e raised to the power iota n plus 1 theta into dz, which is equal to c. Z is e raised to the power iota theta, so dz is equal to iota e raised to the power iota theta. So this is iota e raised to the power iota theta d theta. Now this iota cancelled with this iota, right? And e raised to the power iota theta is cancelled with this e raised to the power iota theta from the denominator. I'm writing this into the next step. This is equal to 1 over 2 pi integration from 0 to 2 pi. This is 1 over, taking a common, 1 minus e raised to the power iota theta over a, because I need to take this in the numerator as the inverse and need to expand. So this is e raised to the power minus iota n theta d theta. Further, 1 over 2 pi a, 0 to 2 pi. This is 1 minus e raised to the power iota theta over a, this inverse, and e raised to the power minus iota n theta to this side, this thing. 2 pi a, 0 to 2 pi, e raised to the power minus iota n theta. Expanding this, I am getting the summation m going from 0 to infinity, e raised to the power m iota theta over a raised to the power m d theta for mod of e the power iota theta over a less than 1. This mod is 1 over a, which is less than 1. Clear? Alright. This we have to write, very important. Without this, we cannot expand, right? This is important to write. Now because it is a GP series, so the series is convergence, uniform convergence. So the convergence being uniform, I can take this sum outside now. 1 over 2 pi iota, 1 over 2 pi a, summation n going from 0 to infinity, 1 over a the power m, 0 to 2 pi, e the power minus iota n theta, e the power iota m theta, d theta. So the convergence being uniform, that's why taking summation outside. Very important to write this also. Fine? Alright. Now this is equal to, I adding the power of e, which is 1 over 2 pi a, summation I'm going from 0 to infinity, 1 over a the power m, integration 0 to 2 pi, e raised to the power m minus n, iota theta d theta. Right? Now check. If n is equal to m, not equal to m, and if n is equal to m. If n is not equal to m means the power is non-negative integer, and for that this integration is 0, right? So I got 0 if n is not equal to m. I explained this in the previous example. Now if n is equal to m, what we get? We get e the power 0 here, and that is 1. So we are left with 1 over 2 pi a, summation m going from 0 to infinity. This is 1 over a the power m. Instead of m, I write a the power n. Right? And then we have integration one over 2 pi a, because summation is for m, but I am taking n to be equal to m, so this is a the power n. Integration 0 to 2 pi theta d theta. So this is equal to 0 if n is not equal to m, and this is integration is 2 pi. 2 pi cancel, so we have 1 over a the power n plus 1 if n is equal to m. Right? So put this value to our function. Thus f of z is equal to summation n going from 0 to infinity a n z the power n, that is equal to summation n going from 0 to infinity. What is a n? A n is, this is nothing but your a n. So this is 1 over a the power n plus 1 into z the power n. That's it. That's all about the result. This is our required fz. Right? So what are the steps? We just have to take our given fz. Right? What are the steps? First, take your given fz, and you know that fz is expanded in the Taylor series because the function is analytic inside the circle. So we write fz as summation n going from 0 to infinity a n z the power n. What we have to do is, what is given in the example, the function of fz on the circle, we use that fz, make whole fz in exponential terms, cancel out the numerator and the denominator, the factors, put the value of fz in your an and the value of z in your an, get your condition, what you got at the end of this result, and then you put this an value to your original fz, that is summation a n z the power n, which is your required fz. Right? Thank you for watching this video. Goodbye. Have a very good day.